So when you design the joint of the foundation system, there are two forces, as I have told, that one is the column bearing pressure capacity, and that is the second one is the dowels. Through the dowels we can transfer the force. So these are the two ways by which I can transfer the column load to the footing. We are discussing about the joint at the moment. So the maximum bearing load on the concrete is defined by the ACI criteria 318, where the bearing force capacity of the column is 0.85 FC prime into area of the column. We multiplied with the phi also. And when the bearing, the footing area is larger than the column area, then you multiplied with the A2 by A1 under root the 0.85 FC prime A1 into phi, and we are able to find out the total bearing strength of the bearing load that can be carried out by the foot foundation. So what is A1 and what is A2? First we have to see that what is the capacity of the footing and the column that to take the column load, and if the capacity is lesser, then we have to provide the more number of dowel bars. So to find out the capacity, we need to find out the area A1 and A2. A1 is the area of the column, and because the supporting element, the foundation, is larger than the column area, so we make a triangle of 1 to 2 and extend into the footing. The area A2 at a certain depth inside the footing is found by spreading the area A1 at a slope of lesser of 2 horizontal to 1 vertical for solid footing and actually available steeper slope on each side. So the concrete present in the larger area A2 around the loaded area A1 provides the lateral confinement to the concrete and causes increase in the bearing strength. So normally what we do is that we spread the area A1 by making a triangle throughout the depth of the footing, triangle of 1 vertical to 2 horizontal, and we see that what is the max area obtained at the bottom of the footing. So that larger area is basically A2 that is obtained at the bottom of the footing. The blue color line are showing here the area that is obtained by spreading the A1. You can see here that in the left hand side footing that is of size 9 by 9, the area of the column is let's say certain area of column is 1 by 1 feet, but when this area was spread into the footing which is only 18 inch thick, the area is quite larger, so that is equal to about 7 by 7 feet. So that brown color lines are showing the A2 brown. The area within the brown rectangle is the A2 and A1 is the area of the column. When the footing width is smaller than the area obtained by spreading the A1, then you have to consider only that part of the footing which is available. So in the right hand side figure, when the footing width is small, so then we have to consider only the area which is available. Similarly, for the rectangular footing, on one side we are getting the area, but on the other side we are not getting the area. So that will be the A2 value. So to find out the bearing strength of the column, the first expression is used, which is given here as in the first equation. To find out the bearing strength of the column on the footing pad, this second one expression will be used, where phi is 0.65 and 0.85 FC prime A1, we will be multiplied by the A2 by A1 under root. And A2 by A1 under root should be less than, actually maximum value allowed is 2. So it should be less than this one, phi into 2 into 0.85 FC prime A1. So by by this expression, we will be able to compute the foundation, we will be able to compute the bearing strength at the bottom of the footing. And now this is the capacity of our available structural components, column and the footing. But now we will see that whether the dowels are needed or not needed. So for that we will see that our 5PN, the bearing strength is larger or the column load is larger. If the column load is larger, the column reaction at the bottom of the footing, that is larger, then you have to go for the dowel bars. And if the column load is lesser than the capacity, then we have to we can provide the minimum dowel bars. So this is the criteria for the dowel bars, that the excess force, which is basically not resisted by the concrete, which is equal to Pu minus 5 Pn, if it is obtained, then we have to go for the dowel bars. And dowel bars area can be computed by the difference of the force, the column load minus the capacity bearing strength on the column divided by the stress in the steel. So this will give us the area of steel of required. So Pu minus 5 Pn over 5 Fy. These we can compute this area of steel because this is an axial load. So that's why to compute the area of steel, the load over stress is this expression is used. This is not the flexure, but the axial force is transferred to the dowels. So then you can, if you see that the minimum dowel bars area, which is 0.005 Ag, so we have to go in any case about for the minimum dowel area, that is 0.005 in the gross area of the column. So 4 dowels are at least needed anyways, but if you need excessive dowel, you can compute from this expression. In addition, we must check that how much is the capacity of the column. So sometimes we can, if the column steel is not extended and the bearing strength of the portion of the column is to be checked. We check that how much dowel area is needed in the column to be developed, because these dowels are not only provided in the footing but also in the columns. So we can compute the load minus the 5.85 Fc prime Ag divided by the stress, and we can compute the area of steel. So dowels must have diameter less than or equal to number 35, and these dowels are extended to the foundations. Now how to extend these dowels, how to develop the steel, you have to definitely refer the chapter of the development and encouragement of the reinforcement and the bar diameter bond strength, because that is the next expression for development length and splice length for the dowel bar is taken from that chapter, ACI 31811, or any code of the any year in 15 chapter. So these are the expression for the development length for if there is a tension, if the steel is in tension, that you have to develop that part of the footing is in tension, so you have to use the tension dowel development length for the tension, and this development length only depends upon the dia of the bar, yield strength of the steel, and the compressive strength of the concrete. So you can compute this using these relevant expressions. Similarly, you will use the development length in compression. So you will use the formula Fy, Fc prime and dB for the development length in compression. And when the bars are in compression, you can use the development length in compression. And tension splice length. Then you have to splice the steel with the column steel, the footing steel and the column steel. So this splice length will also be used. Class B splice are one is the splice is LD, one splice is class B is 1.3 time LD. So we have to see that which kind of splice is in compression or in tension. If the splice is in compression, then we will use this expressions. So every value is clear, and you can use this formulae to compute the required development length and splice length. Then we will splice the reinforcement in the column, like it is shown, the red colored dowels, which is spliced with the column steel by using the splice length formula, and extended to the footing steel also by using the development length expression. So total extension in the footing, not only vertical part but also the horizontal part. Vertical plus horizontal, I mean they are the available length is not sufficient in vertical thickness of the footing, so we have to extend it by bending it at 90 degree. So total extension should be equal to the LD. In tension, if the footing is in tension, so that LD will be used, and in this way you will compute this, complete this joint design. Then the steps involved for the foundations. The steps involved, you have to collect all the information, allowable bearing capacity, depth of the footing, type of load coming, and decide the type of the footing. Then for the service dead load and live load, you will have to compute the allowable bearing pressure and find out the size of the footing by the service load divided by the allowable bearing capacity. Next, you will see that your maximum pressure developed under the footing should be lesser than the bearing capacity. You will compute the pressure as per the requirements, whether it is a moment case, whether it is an axial case, or the two moment case. Then you will compute the ultimate bearing pressure under the footing by the dividing the PU, factored load, divided by the area provided. Then you will select the suitable thickness of the footing and apply the punching shear check, and if it is not satisfied, you will revise. Then you will compute the bending moment in shorter and longer direction and compute the flexural reinforcement. Reinforcement will be provided where there is a tension in the footing, and you have to develop the steel, design then the joints, also the dowel bars, and develop the steel and compute the splice length and development length and provide the steel. These are the center hook detail, which is when we are making the bending the steel or making the hooks. These are the minimum requirement for horizontal standard hooks development length. And then the cases for the rectangular footing, here we are discussing about the changes occurs in the rectangular footing, because all the procedure is same for the design, for computation of the reinforcement, every procedure is same. However, in the rectangular footing, we know that in the central region the force is larger. If you see this figure, how to place the steel in the shorter direction. So in the shorter direction, we are not placing at the uniform spacing, but we are giving more reinforcement in the central region compared with the outer region. The reason being that the load concentration is larger in the central region. So the load in the central region is more, so we have to provide the more concentration in the of the bars in the central region. So criteria is explained by the ACI that the reinforcement in the longer direction shall be distributed uniformly, but the reinforcement in the shorter direction, a portion of the total steel, because the steel is already computed AS, so a portion of steel which is gamma S, which is always larger than 0.5, that will be placed in a bandwidth center or in the center line of the column equal to the bandwidth B, and the remaining area, which is 1 minus gamma S by 2, that will be placed on the both sides of the footing. So gamma S will be computed by 2 over beta plus 1, long side of the column footing to the short side of the footing, and then we can compute place this steel in the central region. The central region is taken, first one case is the one-way footing here, because in one-way footing the main steel is only in one direction, like the wall footing. In that case the steel is evenly placed. But second case is of the two-way footing, isolated footing, then the bars are uniformly placed in the square footing at the bottom left hand side, you can see. But in the rectangular footing, the bars are not uniform placed, but in the central band it is placed closely spaced. So central band is taken as equal to the B value. So total length of the footing is L. In the center B value, we are placing the bars. The area of steel is computed separately as AS1 gamma S into AS. The AS is already computed in that direction, so we will see that, let's say 70% is provided in that zone and the remaining 30% is provided in the other zone. So this figure is further cleared, that you can see that the ASL is further divided into two parts, AS1 and AS2. So the steel in the AS1 part is gamma S into ASL. So gamma S is basically larger than 0.5. So that's why the steel in the central band is larger and the remaining steel at widely spaced bars are provided at the ends. So this is the detailing for the rectangular footing, and minor changes are there for the rectangular footing. These are the flat elastic curve for the isolated footing and combined footing. So I have asked the question that what kind of forces are developed. So when the load is acting upward in the isolated footing, you can see the side view right hand side that the tension is developed at the bottom. It means that the steel that is designed will be provided at the bottom for the isolated footing. And if the thickness of the footing increased a certain limit, then we will provide the top minimum steel. And second case is the combined footing. So you can see that in combined footing, the behavior of the footings are reversed than the beam, because under the column, the tension is at the bottom. So bottom steel is needed under the column, and between the column, the movement is negative because the tension is at the top. So top steel is needed between the columns, and under the column load, the bottom steel reinforcement is needed. So these are the detailing for the elastic curve for the footings. We will start with the problem next. So we have to carry out the different problems. If you have any question, you can ask, and then we can solve with the foundation design problems.